Hi, welcome back. In this lecture, I would like to finish the lecture about quantum phase estimation. I want to provide more details about implementation and the specific quantum circuit we are using for quantum phase estimation. I want to go back to concepts that we've seen before that are used in the quantum phase estimation. So these concepts are the inverse QFT and the phase kickback. So the phase estimation let us extract the eigenphase associated with a particular eigenstate, requiring us to specify that eigenstate with an input register. So the phase estimation requires as an input the eigenstate. We might question how useful it is in practice to use a phase estimation, as in many cases, we do not have the eigenstate, the quantum eigenstate of a particular quantum operator. Well, it turns out that we can actually use the phase estimation quantum computing primitive in superposition. So we can provide a superposition of a state, and then the phase estimation will output all the eigenphases in superposition of states. So the real utility of phase estimation is really that it can work in superposition. If we send a superposition of eigenstates, so a generic input that is in a superposition state, then our phase estimation will give as output a superposition of associated eigenphases. The magnitude for each eigenphase in the output superposition will be precisely the magnitude of its eigenstate in the input register. It turns out is quite useful in the sense that we do not need a priori to know a priori the quantum eigenstate, right? But we can just input a quantum state in a superposition of states, and then we will get as an output the eigenphase still in superposition. So any state of a QPU register can be thought as a superposition of the eigenstates of any Q operation. And therefore, we can actually put any generic superposition of a state. There will be a superposition of the quantum eigenstates. This also means that if we set the control U operator, what we call cont underscore U, to be some QPU operation, U, and the QIN to be some general register quantum state X, then the primitive, the quantum phase estimation, returns the details of eigenphases that characterize the action of U on the X state. Therefore, we can effectively extract all the eigenphases in superposition. And this also raises the possibility of parallelizing this eigenphase extraction. So the real power of the quantum phase estimation is the fact that we can work in superposition, therefore we can work in parallel in extracting the eigenphases of the eigenstates that are represented in generic state X. In this slide, I present the quantum phase estimation quantum circuit in detail. Remember here at the top we have the output quantum register, and then at the bottom we have the QIN, that is the quantum state. Typically it's the eigenstate, but as I said, we can put any generic quantum state. We put the output in quantum register in superposition of a state, and then we have a cascade of a control operation of our U gate. So for instance, in the previous example, we saw the Hadamard gate, control Hadamard gate. So here, instead of U, we could have H. So what is the function of this cascade of a control operation? These gates use the phase kickback, so they will see that act as a rotation. After this block of 2 to the n, so where n is the number of qubits we express our eigenstates, we have the inverse QFT that will allow us to extract the frequency. So here we have a simple example of the code. We applied on Q out the Hadamard gate, and then we apply a cascade of a control U operation, and finally we apply the inverse QFT operation. So how the phase estimation works? So since the phase estimation has access to the QPU operation under scrutiny, and one or more of its eigenstate, why not simply act on equiparation on the eigenstate? So we could start with the eigenstate, apply our U, and then we see basically the same magnitude of the states, but then we have the global eigenphase that is changed. Well, the reason why we cannot use this directly is the fact that we cannot actually read the relative phase or the phase during a measurement. So a global phase cannot actually be read out. So we will need to go relative phase and then apply some inverse QFT like operation. As I said in the previous slides, we could rely on using inverse QFT. The QFT transforms periodic phase differences into amplitude that can be actually read out. So we have to find a way to cause the relative phase in our output register to vary periodically with the frequency determined by our eigenphase. And then after we encode it to our periodic signal, then we can apply the inverse QFT and make a readout. So for the inverse QFT, we want a quantum state of this particular characteristics. So we simply take an equal superposition of all possible register states and rotate the k state by k times, whatever the frequency is desired. That is, if we want to encode an eigenphase of theta, we rotate the kth state by k multiplied by theta. For example, if we want to encode a 90-degree eigenphase in the 8th state of a 3-cube register, as depicted in these slides, we can rotate the kth state of a register by k times the eigenphase we are actually after. We can build a circuit to achieve this kind of conditional notation by combining the control U subroutine with the phase kickback circuit. Every time we act our QP operation U on its eigenstate, we produce a global rotation by its eigenphase. We can extend this idea and apply a global phase that is rotated by any integer multiple k specified in another QPU register of an eigenphase angle. So we will need this control operation to make a phase kickback to provide the right rotation. So every time we apply the U quantum gate to the eigenstate in the bottom register, we rotate by the eigenphase, and this is the phase kickback. The choice of conditional operation performs the number of rotation required by each bit in the binary representation of k, resulting in us applying U a total of k times on our bottom eigenstate register, those rotating by k multiplied by theta. So this is the last slides. I just want to summarize the quantum phase estimation primitives that relies on three important concepts we introduced previously. The phase kickback to provide rotation, construction of control unitaries. For instance, we talk about the control Hadamard or any control operator that we want to estimate the eigenphase. And then finally the inverse QFT primitive to extract the eigenphase. So the quantum phase estimation can extract information that QP operation encode in the global phase of a register that is difficult to directly assess. So to assess, we transform the global phase information into relative phase information in the second quantum register, and then we apply the inverse QFT to extract the information in the readable format. These are the last slides, and talk to you soon.